environment. And any questions or input from the other participants, please be respectful. As you probably just were notified by Zoom, we are recording this webinar, so be aware of that as well. So a quick introduction, what is multi-sector dynamics? Multi-sector dynamics is the study of how complex, built, natural, and socioeconomic systems co-evolve. It's a transdisciplinary research area that seeks to advance our understanding of human Earth system feedbacks. And this webinar today is brought to you by the Multi-Sector Dynamics Community of Practice. This is a group that represents an effort to accelerate development of foundational capabilities through open science and growing a diverse transdisciplinary workforce. This is open for you to join if you're interested, and it's open to everyone. You can join if you have a phone ready. You can join with this QR code on the screen. We'll also be posting the link to join our community of practice within the chat. It's multisectordynamics.org/join us. We'd love to have you be a part of this. And before we get started, I also want to let everybody know that there's another webinar coming up this week on Wednesday at 1 p.m. Eastern time till 2:30. This is a webinar from our early career working group focusing on careers in multi-sector dynamics related field. We have an excellent panel lined up, again, hosted by the early career working group, that will talk about some experiences from folks in early and mid-career. But today we're focusing on the AI working group, and specifically, it's my pleasure to introduce Don Liu, a senior computational earth scientist in computational sciences and the engineering division from Oak Ridge National Laboratory. Dr. Liu earned her PhD in computational hydrology from Florida State University in 2012. Her research specializes in integrating advanced computational methods with artificial intelligence and machine learning to tackle challenges in hydrological and earth systems modeling. Her expertise spans uncertainty quantification, data assimilation, multi-model analysis, data analytics, and development of physics-informed, explainable, and reliable AI frameworks. As a principal investigator, Dr. Liu leads multiple Department of Energy projects, advancing research in areas such as coastal flood prediction, earth system modeling, hydropower forecasting, coastal or geophysical inversion, and geological carbon storage simulation. Her scientific contributions include over 90 peer-reviewed publications and the development of 4 innovative software tools. And in 2023, she received the prestigious Department of Energy Early Career Award. So without further ado, I'll pass it over to Don. And so please take it away. Let me stop sharing my screen here.
Okay, yeah. So I will start sharing my slides. So first of all, thank you, Stephanie, David, and Julian for the invitation, and thank you, David, for the nice introduction. So can you see my sharing? Can you see my slides? Oh, hello, can you hear me?
Yes, and we lost your slides, but they were showing well before.
Okay, so let me start sharing again.
Perfect.
Okay, you can see it right now, right?
Yeah.
Okay, yes. Okay, let's get started. So for joining today's webinar, I'm Dan Liu, a senior computational earth scientist at Oak Ridge National Laboratory. My research focuses on advancing earth system modeling through data model integration, AI machine learning, and uncertainty quantification, as shown in this figure. So the intersection of AI and earth system modeling is one of the most exciting and rapidly evolving frontiers in the geoscience. And as we face the unprecedented environmental challenges, improving our modeling capabilities has never been more critical, and AI machine learning offers a powerful tool. And today I will share some of my work on the explainable AI, reliable machine learning, and AI foundation models for the earth system modeling. And my goal here is to spark discussion. So I will keep my talk to about 40 minutes. and then leaving some time for the questions and the conversation. So understanding and predicting Earth systems are critical for both the society and the environment. However, current observational systems capture only a fraction of the Earth's complexity. Then to fill these gaps, we rely on the Earth system models that integrate the scientific knowledge with the diverse datasets to improve the process understanding, reconstruct the past conditions, and predict the future changes. And our research advances the Earth system modeling by combining the data and models, leveraging the advanced computational methods and integrating the AI machine learning techniques. And the goal here is to enhance the predictions and support the informative decision-making in the changing world. And with more data, better computing power, and deeper scientific understanding, Earth system models have evolved from the empirical models to theoretical models to computational models, and are now transitioning to the data-driven machine learning models and the big data-powered AI foundation models. And in the third paradigm of the computational modeling, we developed physics-based models to simulate a complex Earth system based on our scientific understanding. For example, Department of Energy's Energy Exascale Earth System Model, E3SM, is a state-of-the-science coupled system, including the atmosphere, ocean, land, river, and human components. And for each component, we use the data model integration approach to improve the prediction. Specifically, first, we collect the data and construct the physics-based models based on our understanding. And these models contain uncertain parameters that must be calibrated against the observations to enhance the simulation accuracy. And once calibrated, the models are used for prediction. And if predictions are accurate and have small uncertainty, then the models can be applied for the real-world problems and decision-making. And if not, we refine the models by incorporating more data to enhance the predictive capabilities. And this physics-based model prediction process involves the inverse modeling to estimate parameters and forward simulation to generate predictions. However, the prediction is inherently uncertain, driven by the data quality, model structure, parameter estimation, and initial and boundary conditions. And quantifying and addressing these uncertainties is critical to improving the prediction accuracy and supporting the informative decision-making. Then to tackle these challenges and improving the physics-based model predictions, we developed a comprehensive uncertainty quantification framework. And this framework identifies and quantifies the multiple sources of uncertainty, helping us better understand the modeling limitations and mitigates associated risks. And in addition, we designed a suite of advanced computational methods to improve the efficiency of the uncertainty evaluation, as listed in the upper left corner. And some methods focus on the forward UQ, and while others addresses both the forward and inverse UQ, and making these evaluations practical for the complex and time-sensitive applications. And we also introduce information theory-based approaches to guide the cost-effective data collection and systematically reducing the prediction uncertainty. And these methods have been successfully applied to a wide range of geoscience domains, including the climate modeling, subsurface modeling, land surface modeling, and hydropower system modeling, demonstrating their versatility and real-world impacts. And then with the advancements in the satellite remote sensing and the in-situ sensor networks, researchers are increasingly using the data-driven machine learning models to simulate the Earth system dynamics. And these models leverage the extensive and diverse datasets, opening the new possibilities for the environmental prediction. So as we move into this paradigm, machine learning models, such as long short-term memory networks, are widely used to capture relationships between the environmental drivers and the responses, laying the system behaviors directly from the data. Now, while these models have shown the great success in the Earth system prediction, they also raise the critical questions about the trustworthiness. For example, how can we ensure that machine learning solutions generalize across different spatial and temporal scales? And how do we verify that the models are making good predictions for the right reasons? And more importantly, how can we guarantee the reliability of the predictions under changing environmental conditions? And our research tackles these challenges by focusing on three interconnected areas. First, we integrate diverse datasets with advanced model architectures to enhance the prediction accuracy and improve the generalizability across different spatial and temporal scales. And second, we incorporate explainable AI techniques to validate the model decisions, ensure the physical consistency, and identify the key environmental drivers. And this is not only deepens our understanding, but also guides targeted data collection. And the third, we also quantify the prediction uncertainty to evaluate and ensure the reliability of machine learning predictions, even under the changing environmental conditions. And together, these efforts enable the machine learning-based Earth system models to support multi-sector applications, such as energy and water management, while also boosting the confidence in the predictions. And in the following sections, I will go through each of these areas in detail. And first, let's dive into the first area, how integrating the diverse data with advanced machine learning models improves the prediction accuracy and the generalizability. So as we know, accurate long-term stream flow forecasting is crucial for effective water resources management. However, predicting the stream flow over the extended time horizons remain a major challenge. And then to address this, we developed a temporal sequence transformer, a machine learning model that integrates the past weather observations, future weather forecasts, and the historical stream flow data to improve the 1 month ahead stream flow predictions. And this TST model architecture, as shown in the right figure, includes 2 encoders to process the historical and the future driver data, and 1 decoder to process the past stream flow information. Across temporal fusion module helps denoise and integrate the encoder outputs, while the decoder combines this encoded information with the past stream flow data for the future predictions. And we applied this method to forecast the stream for 30 days ahead at the major US basins. And results indicate that our TST models outperform the process-based hydrological model, like the big model, achieving higher prediction scale scores and maintaining a strong performance, even with a noisy weather forecast inputs. And this study highlights the potential of advanced machine learning models like the TST here in enhancing the prediction accuracy and the temporal generalizability by effectively integrating the diverse datasets. In the pivotal study, we trained a machine learning model to predict the stream flow for specific basins using the historical stream flow data. However, most basins are ungauged, lacking the historical records, and which presents a significant prediction challenge. And then to address this, we developed a regional machine learning model trained on the data from the gauged basins to predict the stream flow in ungauged basins. And to further improve the model training, we incorporate the catchment attributes such as the soil property, geology, and topography. And for basins without the attribute data, we developed a machine learning model like the vision transformer model to extract the relevant land surface information from the widely available remote sensing data. Additionally, we combined all available input data, meteorological forcing, the catchment attributes, and remote sensing information, all this information we have to maximize the model performance. And we applied all these 4 machine learning models to predict the stream flow across the corners, demonstrating and investigating their ability to address the challenges of the ungauged basins. So in the study, we used the CAMOS dataset for the model training and the evaluation, employed the 3-fold cross-validation to assess the spatial and temporal out-of-sample prediction performance. And the results indicate that machine learning models integrating the diverse data from the gauged basins and the satellite images outperform the other approaches in predicting the stream flow at ungauged basins, under future meteorological conditions. This study highlights the potential of the advanced machine learning models that combine the gauged basin data with the widely available remote sensing images to significantly improve the prediction accuracy and enhance both the spatial and temporal generalizability. So beyond achieving the accurate predictions, we also aim to understand why the machine learning model performs well and what are the key drivers contributing to its success. And in one project, we used the encoder-decoder long short-term memory networks to forecast the reservoir inflow a week and a month ahead. And to analyze the hydrometeorological drivers behind these forecasts, we applied explainable AI techniques. And we started with off-the-shelf sharp methods and to evaluate the inflow predictions across the multiple reservoirs in the western and the southeastern United States. And the results aligns with our physical understanding in the snowmelt dominant basins in the western US. Temperature was a key driver of the inflow forecast. And in the rain-driven basins in the southeastern US, precipitation plays a dominant role. And across both the regions, historical inflow consistently emerging as the most influential variables. And these insights reinforce that the confidence in our model's decision-making process. However, sharp method has some limitations. So first, it was computationally expensive. The computational complexity is on 2 power n, where n is the number of features. And it cannot separate individual and the interaction contributions of the drivers. And then to address this, we developed a more efficient integrated gradient methods. And this IG approach not only accelerated analysis, but also provided deeper insights into the individual driver impacts and their interactions. And we applied these integrated gradient methods for the 30-day inflow forecast across multiple reservoirs in the Upper Colorado River Basin and gained a good understanding of the machine learning-driven predictions. And as we know, Earth systems are inherently dynamic, while the drivers have a memory effect on the response predictions over time. And then to better capture this complexity, we go beyond assessing the variable importance to also investigate their temporal importance in the system predictions. To achieve this, we applied a range of interpretable machine learning approaches. And in the attention-based transformer models, as shown in the left column, self-attention mechanisms identify the temporal patterns within each driver, while the cross-attention mechanisms capture the relationships among the drivers. And then by extracting and visualizing these attention values, we can validate the model's learning process and in the meantime, ensure it aligns with our understanding of the system's relationships and the dynamics. And in another study, I show in the right column, so we developed interpretable long short-term memory networks to predict water and carbon fluxes using multiple environmental drivers while simultaneously analyzing both the variable and the temporal importance. And unlike standard LSTM models, which just mix the drivers dynamics within the hidden states, our interpretable LSTM uses a variable-wise hidden matrix. So this design captures the distinct influence of each driver, enabling a more detailed evaluation of how different variables interact over time. And when applied this method to the carbon flux prediction, the results indicate that our interpretable LSTM not only achieved higher accuracy, but also revealed new relationships between the environmental drivers and their memory effects on the carbon flux. And this insight can inform the process-based land surface model development, bridging the gap between the machine learning predictions and the physical system understanding. Explainable machine learning techniques help us understand why a model performs well, but it's also important to identify when and why the model may fail. So especially when simulating a dynamic Earth system under the changing environmental conditions. And machine learning models often struggle to maintain a good performance under new or unseen conditions. So for example, as shown in this figure, an LSTM model trained on the 20 years of data from a relatively cool climate struggle to predict the stream flow during the subsequent warmer years. And this performance drop highlights the key limitations. That is, machine learning models can fail when applied to the evolving climate scenarios. And then to ensure reliable predictions, uncertainty quantification plays a critical role. The UQ can help detect the situations where the model is likely to make poor predictions by flagging the higher uncertainty as a warning signal. So some details here, and despite the UQ is important, however, uncertainty quantification for the machine learning models remains unchallenged. So current state-of-the-art methods comes with trade-offs. For example, the Bayesian neural networks provide rigorous uncertainty estimates, but are computationally expensive. And Monte Carlo dropout and deep ensembles are more practical, but rely on the strong assumptions like the Gaussian assumption that may not always hold. And most prediction interval approaches introduce additional hyperparameters, often leads to the unstable training and unreliable performance. And these challenges highlight the need for more efficient and robust UQ techniques that balance the accuracy, computational cost, and stability. And then to address these challenges, we developed a novel prediction interval method called PI3NN to quantify the machine learning model uncertainty. For a given confidence level, this approach estimates the prediction intervals using 3 neural networks in 4 steps. So first, we train a neural network. So no matter what neural network you want to use, depends on your data feature to estimate the prediction value. And then based on the prediction errors, we train 2 additional neural networks to estimate the up and the lower bounds of the interval. And lastly, we calculate 2 coefficients to precisely determine the uncertainty bound. And we have applied the PI3NN to multiple scientific problems, demonstrating that it produces accurate and reliable uncertainty estimates that can precisely enclose the specified portion of data with a narrow interval width, so support informed decision making. And here is one example. In one study, we applied the PI3NN to quantify the uncertainty in LSTM stream flow prediction for 2 catchments in the East River watershed, Colorado. At the Q Creek catchment, where the hydrometeorological conditions in the test period were similar to the training period, PI3NN accurately quantified the uncertainty, aligning well with the confidence level. However, at the Rock Creek catchment, where the test conditions are different from the training conditions, the machine learning model struggled during the data shift. And PI3NN can detect this shift by producing a wide uncertainty range, and this is consistent with larger prediction errors. And this error-consistent UQ approach is particularly valuable when machine learning models are used to predict future conditions or regions without ground truth data. And then by acting as an error indicator, and this uncertainty estimate helps prevent overconfidence in the predictions and ensures their reliability under changing conditions. Additionally, the quantified uncertainty can guide the data collection and the model refinement to improve the prediction, and where we need to spend more effort to collect the data or refine the model to reduce the uncertainty. So, so far, we have discussed data-driven machine learning models and introduced 3 strategies to enhance their prediction accuracy, interpretability, and trustworthiness. While these models excel at capturing the complex patterns, their performance is often limited by the data availability, weak physical consistency, and poor transferability to the new regions and the conditions. And then to address these challenges, physics machine learning hybrid models have been developed. And these methods integrate physical principles with the data-driven models to improve the reliability and generalization. And the hybrid models can be designed in several ways. So one approach can incorporate the physics as the model inputs to enrich the data, while another can embed the physical laws directly into the loss function to enforce the conservation constraints. Alternatively, physics can be integrated into the machine learning model architecture design, so ensuring a more accurate representation of the natural system. For example, so we can develop a graph neural networks to mimic the natural river systems. And in coupled Earth system models, hybrid approach can be applied in two ways. So they can enhance a single component by combining the larger scale physical models with the process level subgrid data-driven models. Alternatively, they can replace the specific physical components with the machine learning models while coupling with the other physics-based components to simulate a full system. By combining the strengths of both the physics-based and the data-driven approaches, these hybrid modeling strategies offer a more robust and a generalizable way to improve prediction accuracy and also deepen our understanding of the complex Earth system process. We performed several studies using the physics machine learning hybrid modeling, and one such study focused on improving the stream flow prediction across more than 500 catchments in corners by combining the physical modeling with the machine learning. In this study, we developed two hybrid models and compared their performance against both a standalone physical model and a purely data-driven machine learning model. Here is the LSTM. And by evaluating the strengths and the limitations of each approach, we gained valuable insights into these effectivities and the trade-offs. And this understanding helps us refine and develop more robust hybrid modeling strategies for the future applications. And then driven by the availability of the large training datasets and the rapid advancements in the GPU-driven computation, recent years has seen a remarkable progress in the deep learning, particularly with the development of the GPT models, the generative pre-trained transformer. And this transformer model architecture and the self-supervised learning have given rise to the foundation model paradigm. A foundation model is a large-scale neural network trained on the vast, diverse datasets in a self-supervised learning. It can then be fine-tuned for a wide range of modeling tasks. And these models operate in two phases, pre-training and fine-tuning. And it relies on four pillars: data, model, compute, and applications. And during the pre-training, the model learns a general representation of the Earth system by processing the large heterogeneous datasets. And it's then fine-tuned using the limited observational or the simulation data to adapt to the specific modeling tasks. And these models are typically very large, often with millions or even billions of parameters, allowing them to effectively process the massive datasets. And their performance generally scales with the data and the model size. And while the pre-training is computationally intensive and usually requires supercomputing resources, fine-tuning is relatively fast, making it practical for the real-world applications. And once trained, the foundation models can be leveraged for a variety of tasks, including the short-term weather forecasting, long-term climate prediction, climate downscaling, and even accelerating our physics-based numerical model simulation. These capabilities make the AI foundation models particularly well suited for our Earth system modeling. And as we know, the Earth system generates vast and diverse datasets from the in-situ measurements, remote sensing, tabular database, and numerical simulations. And these datasets have multiple types, multiple scales, and multiple resolutions, making the full integration challenging for the traditional numerical models. Additionally, much of this data remains unlabeled, limiting its usability for a task-specific supervised machine learning. And recent advancements in the vision transformer architecture allows us to integrate these heterogeneous datasets, and their model performance has been demonstrated improving as the data volume and the data resolution increase. And more importantly, Earth system simulations have broader scientific applications and impact multiple sectors. and making the foundation models as a powerful tool for advancing research and decision making. And by fine-tuning the pre-trained foundation models, we can enhance the modeling tasks while reducing the computational cost, also reducing our individual efforts and the energy consumption. And at the same time, leveraging the broadly trained foundation model can also improve the prediction accuracy and the generalization. So I would say this paradigm shift has the potential to revolutionize the Earth system modeling. And right now, the foundation model is still at its earliest stage, but it's a very exciting area. And we are currently developing a foundation model for the Earth system modeling called Orbit. Orbit is pre-trained on the CMIP6 climate simulation data, leveraging the ESGF for data access and the PMP package to select the high-quality data for training. And it incorporates 91 variables, including temperature, wind speed, humidity, and the geopotential, spanning the surface to the 17 atmospheric layers. And to explore how model performance scales with the data size and the computational cost, we have designed 4 versions of Orbit, ranging from 100 million to 100 billion parameters. And this evaluation can help us optimize the scalability based on available data, computing resources, and the accuracy requirements. And this also makes the Orbit the largest AI model for the Earth system modeling to date. And our evaluation indicates that, as shown in the bottom figure, the larger models are more effective at processing the vast datasets and capturing the complex patterns. And given the petabytes of the simulation data available from the CMIP project, Orbit can leverage this large volume of unlabeled data during the pre-training phase, and then reduce the requirement of the labeled data in the subsequent task-specific fine-tuning phase, while also accelerating the simulation. And to accelerate the training of this large-scale model, we implemented a hybrid parallelism, combining tensor, pipeline, data, and the sequence parallel techniques in an orthogonal design, and optimized its scalability on our ORNL's frontier supercomputer. And Orbit has demonstrated a strong scaling efficiency of up to 85% across more than 6,000 frontier nodes, ensuring the efficient use of the computational resources. And this exceptional scalability enables Orbit to rapidly generate large ensemble simulations, which are critical for the uncertainty quantification and capturing the low probability extreme events. And in one test, we fine-tuned the Orbit with the ERA value analysis data for the weather forecasting and demonstrated competitive performance against the state-of-the-art numerical model, machine learning model, and the foundation model. And after training, Orbit can produce the forecast in less than a second on a single GPU, making it possible to run the weather forecast on our laptop and rapidly generate large ensembles for the probabilistic forecasting and prediction. Besides the weather forecasting, we are currently fine-tuning Orbit for the weather and climate downscaling, a critical process that converting the coarse resolution weather forecast and the climate model projections into the high resolution data needed for the regional impact assessments. And this finer scale information is essential for the, multiple sectors, including the water resources management, infrastructure planning, and disaster risk mitigation. And we know that the weather forecasting is a temporal simulation problem, but downscaling is an image super resolution problem. And then to adapt the Orbit to this dramatically different task, we replace its embedding layers and its prediction heads, while retaining its attention layers in the middle and the variable aggregation module. Then by leveraging Orbit's pre-trained model foundation, the fine-tuning becomes significantly faster and more data efficient. And our preliminary results are promising, so demonstrating Orbit's potential to enhance the climate downscaling and support critical decision makings across the multiple sectors. And the development of orbit has earned recognition as a Golden Bell Prize for the climate modeling finalist and won the Top Supercomputing Achievement Award, highlighting its impact in advancing the AI-driven Earth system modeling. And this work is still ongoing. Beyond the applications in weather forecasting and climate downscaling, we are exploring orbit's capabilities for accelerating the physics-based Earth system models like the E3SM here. And within its scalability and adaptability, orbit presents significant opportunities for advancing Earth system modeling. So we have the potential, but still a lot of work to do. In addition to developing the orbit for the Earth system modeling, we are also building a foundation model for the natural hazard assessment and the response. So natural hazards such as the floods, landslides, and wildfires are becoming more frequent and intense, increasing the demand of the advanced predictive models that can enhance the disaster preparedness and response. Then to address this challenge, we are developing an AI foundation model that integrates multimodal data from the remote sensing, in-situ measurements, and the building infrastructure datasets to improve the flood prediction, land cover monitoring, and the global mapping of the building environment. And this multimodal learning allows us to overcome the data quantity and the quality limitations across the different sensors, and also improving the learning effectiveness and the prediction generalizability. For example, if you recall in the first study, when we talk about the data-driven machine learning models, we demonstrated how integrating the in-situ observations, catchment attributes, and remote sensing data can enhance the stream flow prediction across the corners. And now, with a foundation model approach, we can take this further. So by leveraging the pre-trained knowledge from the vast unlabeled multimodal datasets, we can significantly reduce the dependence on the labeled data, allowing us to predict the stream flow in ungauged basins with limited observations. And then by fine-tuning this foundation model for the task-specific applications, we aim to provide more accurate, scalable, and generalizable predictions of the natural hazard impacts across the multiple sectors. So specifically for the energy and the water management sectors, we are developing a probabilistic seasonal hydropower forecasting model to enhance the long-term planning and resources allocation. And this model integrates meteorological, climate, satellite, geospatial, and in-situ data with advanced machine learning techniques to predict the monthly hydropower duration up to 1 year in advance. And this forecast can be generated for both individual hydropower plants and aggregated energy regions across the US, providing valuable insights for the grid management and also the reliability. To achieve this, our machine learning framework, as shown in the right figure, uses multiple encoders to extract the key patterns from the diverse datasets and the graph neural networks to facilitate the information sharing across the climate and hydrological similar regions. And this approach through the data fusion and transfer learning improves the forecast accuracy, enhance the regional adaptability, and support the decision-making for both the water resources management and energy production planning. Okay, so far we have discussed several machine learning models and the AI foundation models for the diverse applications in the Earth system modeling. Our methods are designed for the broader applicability, and we support the research community by developing the open source code packages with a comprehensive documentation and demonstrations. For example, so in the left column, one package uses conditional generative AI to quantify the parameter uncertainty and generate the probabilistic forecasts. And this approach is both computationally and memory efficient, enabling the real-time large-scale model calibration and uncertainty quantification. Another package, as shown in the right column, focuses on the quantifying uncertainty in machine learning model predictions and identifying the out-of-sample regions. It produces uncertainty estimates that aligns with the confidence level and also aligns with the prediction errors. And this method has been successfully applied across various neural network architectures and demonstrated across multiple scientific domains, as shown in this figure. And through these open source tools, we aim to advance reproducibility, foster collaboration, and accelerate innovations within the broad research community. Okay, this is my last slide. So this slide summarizes our research on advancing Earth system prediction through the data model integration across 3 modeling paradigms: the physics-based numerical models, data-driven machine learning models, and the knowledge-informed AI foundation models. And each approach has its unique strengths and limitations. And our research integrates data and models, leveraging the advanced computational methods and AI machine learning techniques to enhance the prediction capabilities. So through these efforts, we aim to advance the scientific understanding and also support the informed decision-making across multiple sectors. So I'd like to stop here and thank you for listening. I'm open to any questions.
Wonderful. Thank you very much, Dan. That was excellent. So if anyone has questions, please put them in the chat, and then Stefano and I will read them out to Dan. So we'll give you a couple of seconds to formulate some questions. Otherwise, we can start off with a few. I don't see any yet. Stefano, do you want to start with one?
Yes. So yeah, I'm just resharing the message of please feel free to drop your question in the chat. So while we wait for questions to appear, maybe one question, Dan, and thanks again for the webinar. It was great. I have 2 questions. So let me start with one. Can you maybe share a little bit more about what are some of the challenges with orbit?
Oh, right. So let me go back to the orbit slides. So, okay. Right. So the challenge of orbit, as you can see, we have, yes, this shows model size. We have the 4 model sizes start from the 100 million to the 100 billion. That's because we have a large number of data, and we pre-trained using the CMIP6 data. So those are the model simulation data. And we have a petabytes of the CMIP6 model simulation data. So we need design a large model to extract the information from this large number of data. So since we have this large size of model, so pre-training takes a lot of effort. So that's why to address less efficient training, so we designed a comprehensive scaling parallelisms that merges tensor pipeline data sequence parallelism and get a good and efficient results. And then this is from the pre-training, and then move to the fine-tuning. So we have the most challenges here. So in this one fine-tuning case, we demonstrated the orbit for the weather forecasting. That's essentially predict the weather to the 2 weeks and 1 month out. So, and then as you know, so for the temporal forecasting is essentially the autoregressive or roll-out problems. So we can do a good job, as you can see in these bars, in the near term, but when you forecast it in a relatively long term, up to the 2 weeks or the 1 month, the prediction accuracy decays very fast because it cannot carry over the information from the previous data. And then this is just for the weather forecasting regime. And when you extrapolate it in the climate, such like a decadal a centennial range, it's not it cannot do it just by laying the information from the ERA 5-year analysis data. We need to consider more information, such as from the ocean, like the sea surface temperature, and the climate oscillation related variables. Like a recent development on the ACE models, they did a great job in that. So, right, a lot of challenges, but it's also exciting areas. And since the one advantage I would say for the orbit is foundation model. So besides for the weather forecasting, it can also apply it for the downscaling. As you can see, this is still ongoing work, but we do see promising results to downscale from the coarse resolution to high resolution. So the purpose is here, no matter what the coarse resolution, like Google's developed the GraphCast or GenCast, they can forecast in the following 10 days give a very good results, even better than the numerical models from the ECMWF. But the resolution is very cost, like a quarter degree. But it's not useful for our regional natural hazard investment. So we need high resolution data. So this is for that purpose. No matter what the GraphCast or GenCast give us, we can downscale it for file resolution for our regional modeling assessment. So right, and another we are ongoing is to use the orbit to accelerate the E3CM model simulations. So a lot of going to do by leveraging this foundation.
Got it. Thank you, Dan. So we have the first question here. Two questions. Maybe Dave, I'll go with the first and leave you the second. And so the first one is about the uncertainty framework, and the question more specifically is about how you handle missing data in the input and output without performing gap filling or with gap filling as well.
Yeah, right. Good question. So there's two parts of the question, right? One is the uncertainty quantification. The other is about data quantity, missing data.
No, actually they're together. So how do you, in the uncertainty framework, how do you handle missing data in input and output?
So may I ask which uncertainty framework? I talk about the two uncertainty framework. One is related to the physics-based model. The other is more specific for our PS3 method to address uncertainty for the machine learning models.
Well, I guess it's a good point. Well, to clarify that, maybe we'll add the person Jacopo Ferrario that asked this question. Please feel free to unmute yourself and clarify if you want.
Right.
Yeah, thank you. Well, I don't know which the two. What's the difference? Sorry, between the two. I thought there was one answer to the framework.
Okay. So is this one, are you talking about for the uncertainty for the machine learning models, or I give a uncertainty framework at beginning to show that this one is basically for the physics-based model predictions. So they
for
have
the
different
machine learning
uncertainty.
one, for the machine learning one.
For the machine learning one. Okay.
Yeah.
Okay.
Yeah,
right. So right. This is we want to quantify the uncertainty of the machine learning model predictions. So we use the prediction interval method. Essentially, besides give the deterministic prediction value, we will calculate two additional values to get the upper bound and the lower bound, so to quantify the uncertainty. So, and this uncertainty can separate the aleatorial uncertainty and another is associated with model structure uncertainty. So aleatorial uncertainty can come from the stochastics of the data. So right, the data quality we can capture it, and then for the missing data, so we can either use that's associated, not actually associated with the uncertainty quantification method, associated with the machine learning model, how you want to learn from the data. So if your machine learning model cannot deal with the missing data, like long short-term memory networks, they deal with time series data. So we probably want to do some pre-processing, do the data filling first. So give it a complete time series, so to enable the better learning of the LSTM model. And then if you want to use the more advanced machine learning model, like a transformer model, it can deal with the missing data because it tokenizes it. You should not need to give it a complete sequence of the time series data or regular image from your science. So it can be missing data there, and then the transformer model can deal it well. But if you do have some data quality or data quantity issues, our machine learning model, our uncertainty quantification method can quantify its uncertainty. So it's a combined uncertainty because it focuses on the prediction uncertainty at the end. Hopefully that answers your question.
Yes, thanks a lot. Very clear answer. Thanks.
Okay, thank you.
Well, and our next question was from Jill. Actually, Jill, if you want to unmute, you can just ask it yourself.
Hi, Dan. Really cool talk. This is awesome. So my question for you is, will the AI Foundation for Natural Hazard Assessment include regional procedures for response? So policies and practices that are put in place for areas that experience natural hazards often, such as New Orleans, Houston, Miami, etc.? And that's kind of focusing on the response aspect.
Yeah. Excellent question, Jillian. So, right. So, that's essentially one of the motivation we want to develop these comprehensive machine learning models to consider the heterogeneity between the different regions and considering the different decisions or policy related across the regions. That's why we want to synthesize all the data we have, and then let the advanced machine learning model to learn this to learn from this data. And as you can see in this figure at the bottom, so we also use the graph networks to leverage the transfer learning techniques to learn the similarities between the regions, and hopefully also learn the similarities between the actions or the policies. So then to inform that the regions policy making lack of the data, right? So that's our eventually goal, but we are still working on it, and we don't have solid results to demo to you right now. It's a newly funded project. Yeah, thank you, Jillian.
Thank you so much.
Excellent. We have another question from Hisham, who says, thanks for a great presentation. Can users customize the orbit model for specific applications by feeding their own training data, or is it strictly limited to the global data set it was originally trained on?
Oh, very good question. So probably I can use this figure to demonstrate it. So definitely, so here, as I answered the previous question, we are using a vision transformer model. Vision transformer model, you can feed in any data size. Here, the data is shown globally, but if you want to focus on the North America, so you can just cut it, associated regions, and then tokenize these images input into our pre-trained machine learning model, and then to for your own purpose. And as you can see, here, but you do need to change a little bit as the input layer and the output layer for your specific purpose. But in the middle, the trained vision transformer, you can use our pre-trained ways. So which means you can use a smaller number of the labeled data associated with your specific task. You can get better results by leveraging our pre-trained base. So the orbit model, currently we didn't release it yet. So yeah, we do have a lot of requests, but after we release, we need to go through a lot of processes, but eventually we will be released it with a lot of demos. Yeah, thank you. The short question is yes, it's doable.
There is one more question for you, Dan. So following up from Jacopo Ferrario from the previous question. So in your experience, could an ED-LSTM be used to perform seasonal hydrological forecast?
Yes, another good question. So that's something we are actually doing right now. So I think in one example, we use the ED-LSTM to predict the 30 days ahead, get good results. And then right now this is using the ED-LSTM and for the 1 month ahead forecasting. And then we are working another one using the future TSG. Yes, the temporal sequence transformer. We are comparing these methods right now, and based on our current observations, so our temporal sequence transformer performs better than the ED-LSTM, especially for the long-term forecasting. But also, the ED-LSTM is a relatively simple model with fewer training parameters, and the temporal sequence transformer is a complex model with more training parameters. So if you have a fewer number of labeled data, I suggest you want to use the ED-LSTM. But if you have a large number of data, probably you can try the advanced transformer models. Okay, hopefully that answers your question.
Excellent. Well, we're right up at the hour, and so we want to be conscious of everyone's time. So thanks again, Dan, for that excellent presentation, and thanks everyone for attending and for all the great questions. I want to remind everyone that this webinar, like most of the MSD Community of Practice webinars, will be available on YouTube. So if you want to revisit anything from Dan's talk, you'll be able to find it. It'll probably be up in a couple days or maybe by the end of the week. So thanks again for coming, and we hope to see you at future webinars.
Thank you.
Thank you. Bye bye.
Thanks, everyone.